Wow. It is so good to be here, and I am thrilled that I was able to step up and do this talk. To echo the more accomplished Alan's thoughts, this community is really what makes Go one of the best, if not the best, programming language that I'll continue using for my entire career. Um, so, something I noticed while preparing this talk was that it's not only the 10th anniversary of GopherCon, but it's also my 10th year of programming Go professionally. So it's of particular significance to me. About that time, 10 years ago, I found myself really studying distributed systems and how to build and operate scalable systems. That led me down this observability rabbit hole in which at that time, long time ago, there wasn't like a super standard metrics interface or tracing interfaces. The thing that was really popular at the time was collecting your logs centrally so that you could process them and see what's happening in your systems. So at that time, I learned about Logstash, Flume, FluentD, Graylog, Syslog, and Splunk, and how they all worked to understand what the benefits are, what the trade-offs are. And what I didn't know at that time was that I was about to accept a position at Cloudflare working on and building one of the largest logging pipelines in the world. Of course, any of you who follow Cloudflare know that it's written in Go. But when I started there, they were basically like, here's the keys to the Porsche. Good luck. So I was starting and saw that there was like millions of events per second being processed, and I was suddenly responsible for keeping it online. So shortly after that, I went to Segment where I worked on similar things, just having to do with event processing. So I worked in the core data pipeline where we did some more sophisticated transformations, but it wasn't quite the same scale. But now I've taken the learnings from both of those experiences, and now I'm building Run Reveal, which is a security data platform with the goal of helping security teams detect threats in their corporate infrastructure by processing the logs from various SaaS applications, the security logs, the audit logs, from things like CloudTrail and Google Workspace logs. Before I get too deep into this, though, I'd like to leave you with this little nugget of wisdom that my former manager imparted on me. I'm just going to read it out. He said, imagine you're an ant in a snow globe the size of Jupiter, and you've been tasked with catching every snowflake and sorting them by size and shape before they hit the ground. That is truly the experience of processing data at scale. Now, this is like kind of a funny quote, but the thing that stuck with me was that when you're building these really big systems, the thing that you have to channel constantly is simplify. You have to simplify everything that you're building to its smallest possible component, and then you can build and expand on that. And if you can do that, then you can really start to wrangle these large distributed systems problems that are really difficult to manage. So in this talk, we're going to be talking about this library called Kawa, which is the stream processing library that we use to power everything at Run Reveal. We'll talk about why I wrote it, how it's used, and the design and the implementation and how it brings it all together. But first, I want to take a step back and formally define what stream processing is in the context of this talk. Stream processing is a system which processes a continuous stream of discrete events consuming from some source external to the system and delivering to some destination external to the system. And those externalities are key here because that's what represents the where the errors are going to be encountered most frequently and where you actually have to be very mindful of how you handle those things. Also, I'm probably going to use the terms events, logs, and messages interchangeably throughout this presentation to mean the same thing. And I have to apologize for that. I've been reading way too many implementations of these various log systems, and they just all get mixed up and they all use their own words for it. But all of those mean like the discrete event that we're going to be talking about. So the library is called Kawa. Why would we write another framework? There's so many out there. Honestly, like most of them weren't written in Go. Most of the logging systems, in addition to the logging systems I mentioned earlier, at Segment and Cloudflare, I also looked at Flink and Spark and Druid and a lot of these other stream processing systems that are written in different languages. They all had some drawbacks, a lot of them having to do with the operational complexity. So ultimately, though, Cloudflare was a big Go shop. Segment was a big Go shop. And we found we could be really effective writing these really small purpose-built stream processors and go a long way with it because Go has a tool chain that makes it really easy to optimize. There is one project that's written in Go that I think is worth mentioning, though. That's Benthos, written by Ashley Jeffs. Ashley, if you're watching this, I'd love to talk to you to discuss kind of the trade-offs between the two systems. But unfortunately, when I learned about Benthos, it didn't have the same plugin architecture that I was really looking for. And on top of that, generics are going to be a key part of Kawa. I picked it up pretty much when generics were just getting started in the change request. So I really wanted to make that a core feature of this library. Also, Benthos, as a side note, is now Red Panda Connect. It got acquired, and in typical OSS fashion, it's been forked, so your mileage may vary. But also in typical open source fashion, having worked at startups my whole career, I am definitely leaning into don't let perfect be the enemy of good enough. This library, it's still in pretty heavy active development. I think the core interfaces are not likely to change, but I will say that some of the additional features, the batteries included features, may have some things that change about them, especially behaviorally. So if you are watching this talk and this sounds interesting to you, please come talk to me. I'd love to hear your feedback and get an idea. I want to build this library so that it's desirable for everybody to use. So please come to me with feedback if you have it. So it's really important, I think, to think about the goals before you go into any major project and what you're trying to do. Otherwise, you might get lost in the weeds a little bit. So the goals for Kawa are, number one, be really fast. And what do I mean by be really fast here? I mean, we should be able to process at least 100,000 events per second on a single processor for simple workflows. So a simple workflow would be something just as simple as shoveling data from Kafka into a database or what have you. I also found it really important that it should be really easy to write plugins. So making the plugin interface as simple as possible was a high priority because I've written these so many times that I don't want to spend a lot of time having to think about how to write another plugin. I just want to like regurgitate all of the things that I already know how to do. Additionally, we want to be able to support many different data types. So oftentimes, like you're dealing with data that has different shapes, and I don't want to have to rewrite the queuing library in order to work with a new data type. And we'll talk a little bit about some benefits we get from that as well. I wanted it to have batteries included features, so things like being able to easily write to batch systems, and also there's a processor function or struct that you'll see later on, which really handles a lot of the shoveling of the data from sources to the handlers to the destinations. And then finally, I wanted to ensure at least once delivery guarantees. We're not going to get too deep into distributed systems and delivery guarantees because that's a whole 45-minute talk in itself. But it needs to be at least once so that we know that we've received the data and we're not dropping any. So likewise, the non-goals don't want it to be slow, of course. The next thing is we were not going to adopt directed acyclic graph execution. And so the word salad of Basically, the systems like Flink and Spark allow you to join streams, which really increases the complexity of implementation and operation. So we're really just focused on making these kind of single purpose Go programs, which consume from a source and write to a destination. And then exactly once deliveries. Has anybody used a computer before? Do you know how much they fail? Exactly once is a pipe dream and can often be achieved just by using at least once and resolving duplicates at read time or some other time. So it was definitely a non-goal for this. So this is run reveal. We have dozens of different sources already. We want to try and build them as quickly as possible, as I mentioned. These are all plugins to Kawa. And I just wanted to talk a little bit about my experience and how it has informed Kawa. In my experience, there's no perfect queues out there. They've all got major trade-offs. So it's probably not the best idea, for example, to start with Kafka if you're just getting started on a project. It's got a very large and sophisticated API, and while it is one of the most scalable and reliable queuing systems out there, there's a good chance that you probably want to start with something simpler. And as a company evolves, the business needs change as well, so you might need to evolve your thinking about which queue you're going to be using. So by using Kawa as a library, you can very easily switch in and out those different queue implementations. Also, again, we need to support multiple types, serialized types, to be able to interact with this number of different plugins. So I wanted to start out by just going through a very concrete example. So what I've done is I've written a folks greeter. So we have a folk here. They have a name and a preferred language. We can put the folks in a file, which is a serialized line delimited JSON file. And then we're going to greet them according to their language preference. So we have this greetings map here. And this is pretty much a full example of how you would actually use Kawa. What it's doing is it's instantiating a source, which is reading a file. The events get broken down by the new line delimited JSON. And then we're using this JSON folk middleware to actually deserialize the byte slices that are coming from the original source, which is a scanner-based source. And so the resulting type that we actually get in our processor is the folk object or struct. And from there, we can pass that into our handler. And our handler is going to actually process and select the greeting for the user and send the greeting as a string or as a byte slice in this example down to the printer destination, which simply prints the event out to standard out. And this is what it looks like when you run it. No surprises there. Now, it may come as no surprise to you if you're at GopherCon, you're probably hearing this ad nauseum, but this library was really inspired by this talk that Rob Pike gave on concurrency is not parallelism. So concurrency, not parallelism, is what leads to the fast programs. Parallelism, if you apply it without care, can easily lead to situations where you've got a lot of contention and slower programs. But by applying concurrent design patterns, we can break down the hard work and parallelize the individual components to optimize the slowest parts of the pipeline. So these are the three main components where we're actually doing the concurrency here. We've got sources doing work consuming from external sources. We've got the handlers, which are actually doing something useful with the data, and then destinations where we're sending the data. And this is what it really looks like at run reveal, which we're consuming from all of these different sources. We're multiplexing them, going into the processor, and then handling them, doing things like validation, transformations, and enrichments before sending them out to the customer's destinations. Now, it's important to keep in mind that this is still data flowing through our pipeline, and this is the core message type that kind of underlies all of the data flowing through a Kawa process. You'll notice It's simple. It's just a message, generic, of course. The key is useful for doing things like deduplication, like I talked about earlier. So every message can have a unique ID. The value is the generic type, and it's just kind of a data container. And then the topic is the topic that it was consumed from the source, if it exists. It's useful in situations where you might want to figure out how you're going to deserialize the data, for example. And importantly, I chose a concrete struct here instead of an interface because I believe that a struct really allows you for more flexibility, and it's a lot easier to debug when things go wrong. Whereas an interface, you have to go back and figure out the source implementation of that. So I really leaned into that. And then finally, for the attributes, I chose a context-like API so that you could very easily be able to weakly couple like some source information down in the pipeline where you might not, some consumers might care about it, some might not. For example, a Kafka partition offset, you could encode into attributes and not have a hard dependency on that offset inside the message itself. So it's pretty extensible. Now we're getting to the good stuff. Sources are kind of the core of how we load data. They have a single method called receive, which accepts a context. This is a apparently blocking source. When I say that, I mean it's when you call receive, it will block until there's a message ready to return. It won't return before that. But it has context for cancellation. That func return parameter is the actual acknowledgement function. So you call that once a message has been successfully delivered to the destination, and that's how we ensure at least once verification. And then an error if anything happens while trying to consume that message. Then we have source func, which it works similar to handler func in the HTTP package. So anything that matches that signature can be used as a source. Next, we have destinations. Likewise, this is a blocking or apparently blocking call to destination. Takes a context for cancellation again. The acknowledgement function gets passed in here so that the destination can hold the responsibility for saying to the source, yes, I've successfully committed this to the destination. You can now free that, that message and mark it as acknowledged. And then it also takes a slice of messages so that, you know, when I was building this, I found that there are certain situations where you might want to fan out messages to a lot of different destinations. And so I found that useful as well. So somebody might, seeing this API, might wonder, why not just use channels directly? Well, this is some code, some pseudocode from Sarama, the popular Kafka library from Shopify. And personally, I find it very difficult to reason about channels that are exported. Channels have a bunch of semantics that are associated with them that have to be known up front before you can effectively utilize them without running into contention issues or deadlocks. Things like, is the channel buffered or unbuffered? Who's allocating it? Who's closing it? And perhaps most of all, how do you handle errors? So the errors here in Sarama are handled out of band, which can be useful in some situations, but in a lot of the situations that I've encountered, I prefer to have the error directly associated with the message and being returned from the source at least. So it also, if you're trying to build something that's really reusable that supports middleware, it's really hard to build middleware when you're dealing with exported channels, because then the middleware has to implement some channel semantics of its own, and you can't just easily drop in something there that looks synchronous. Next, we've got the handlers, which are really doing the bulk of the work here. Notice in these handlers, we've got two different types. So those type parameters could be the same type, and it is for the built-in pipe handler. But in practice, there's a lot of situations where you want to do some amount of transforms before you write it to a destination. And so this enables that use case. And also on the handle signature, we're returning that list of messages again. So if you want to drop messages, you return a nil list. So that would indicate to the processor that, hey, there's nothing here that needs to be written to a destination. You could acknowledge it and move on. Or you can send more than one message if you want to fan out something. Handler func, again, has the same principles as handler func in Go HTTP. So this is the core loop for processing in Kawa. So what's incredible here is we're simply just calling the functions as they come and processing them as they go. What's nice about having a loop that looks like this is we can now trivially parallelize this function and be processing, calling receive as many times as you can on the source, as long as the source is able to keep up. And you're passing things into handle ideally being idempotent. You shouldn't necessarily be tracking state in there, like you can. But in a lot of the situations that we're building for, it's mostly just going to be an idempotent operation. And then after the handle, we make that decision about whether or not we're going to call the destination or not. And then we send to the destination the messages that are there if they're there. So that's pretty much the core of the library, but I think it'll be useful to look at a concrete implementation of how you might do this. So last Friday, I was, most of our sources and destinations at Run Reveal are closed source, but I really like Redis and Redis streams, so I decided to take a stab at implementing a source and destination in Redis. And here we have pretty much all the code that you need for a Redis destination here. Essentially, it takes that slice of messages, it iterates over them and publishes them to the Redis stream given by the topic in the options that's not displayed here. And then we acknowledge upstream saying that they've been successfully written. Now, there's some trivial improvements we could do here, like adding batching. If we added batching, then we would be able to launch that in a separate Go routine. But I think this really demonstrates how easy it can be to write useful plugins from the start. Now, Redis also could be a source. So here's the receive method, and you'll notice it immediately drops into a select statement, waiting on context.done to see if it needs to cancel, but otherwise listening to this private unexported channel called message C, and that's holding the message and the act that we're going to be passing back. And here's the actual receive loop that's batching requests to Redis. And so this separation here is really what's enabling that concurrency. While we're fetching a batch to Redis, we could also be processing the events and sending them to a destination. So we have these different Go routines doing different work, but we're not blocked on network I/O because we can do something else at the same time. And so here we're fetching a batch of messages. We define the acknowledgement function. So we're creating the callback for the destination to be able to tell us when everything's been written successfully, so we can free those resources and mark it as processed in Redis. And then we're sending that message back on the channel that we were originally listening on from the receive method. This is concurrency in action, and it works really well for our use case. So I was talking about batteries included functions. We have this flusher or this batch destination, which can take any like imperative destination and turn it into a batched asynchronous destination. And it's a really easy to use API, but generally it just takes a list of messages and it handles the batching and the flushing for you according to the batch size and the time that you configure. And then finally, I did want to go into that original middleware that we talked about. So this is the serialization middleware that you can implement using this. It's made a lot easier by the receive signature. And by doing that, we can serialize any data type and use any source that exposes a byte slice. So middlewares are good for serialization, but can also be used for things like metrics, routing, authentication, caching, and those sorts of things. So what did I learn from all these years of writing these systems? Primarily, like exposing channels across package boundaries really introduces a lot of questions about how it should be handled. Um, but also, of course, Go generics are great for serialization use cases in particular. Um, Also, related to the channels being exported, synchronous and blocking APIs make it a lot easier to implement middleware and allow for broader code reuse. But perhaps most critically, in the vein of concurrency is not parallelism, when you're batching at the edges of your program, that really helps improve the efficiency of the program. So things like TCP congestion control, IO U-ring, Kafka consumers, they all are actually batching internal to their systems, but expose kind of this basic interface to be able to write things to it on a per message basis. And so, yeah, if that sounds interesting, I'd love to chat with you. I've got some stickers. This is Kawa, and it's powering all of Run Reveal. And yeah, if you like it, come talk to me. If you hate it, come talk to me and tell me why. Thank you.